The expansion of the universe is not a state of eternal stability, but a countdown. Our current understanding of physics suggests the cosmos is tracking toward one of three specific, final outcomes. We know the universe is currently expanding. For decades, astronomers assumed this expansion was slowing down. The logic was simple. All the mass in the cosmos exerts gravity, and that collective gravitational pull should act like a brake on the expanding universe. But in 1998, observations of distant supernovae proved the exact opposite. The expansion is actually accelerating. An unseen mechanism is pushing space apart, fighting against the inward pull of gravity. We call this repulsive effect dark energy. How our reality ends is the mathematical consequence of whichever force ultimately wins this cosmic tug-of-war. Our ultimate fate remains unknown because it hinges on a single hidden variable: how dark energy will behave in the future. The first scenario assumes a steady state. If the strength of dark energy remains constant, it wins a slow war of attrition against gravity. As the universe expands, new empty space is created. That new space contains more dark energy, which pushes things apart even faster. Eventually, galaxies will be driven so far apart that their light can no longer reach each other, plunging our local neighborhood into an isolated void. This chart plots the exponential growth of empty space against the severe drop in cosmic density and temperature. As thermodynamic decay, or entropy, takes over, the gas clouds required to forge new stars will be exhausted. The last remaining suns will slowly cool and permanently burn out. Fast forward roughly 1 Google years, and even the supermassive black holes will evaporate. All usable energy will be gone. Constant dark energy results in the big freeze, or heat death, a dead, featureless void where no further work or activity can ever occur. A second model considers a more volatile variable. If the density of dark energy amplifies over time, it becomes what theorists call phantom energy. In this scenario, the outward push grows so violent that the expansion of space itself eventually outpaces the speed of light. Gravity is overcome at the local level. First, galaxy clusters are pulled apart. Then, the accelerating space invades individual star systems, and planets are forcefully ripped from their orbits. In the final fractions of a second, the super-accelerated expansion tears apart atomic nuclei. Ultimately, the causal foundation of space-time itself is shredded. In a Big Rip scenario, the runaway expansion of space shreds the gravitational and nuclear bonds that hold matter together, leaving the structural foundations of reality in total ruin. The third possibility flips the equation. If dark energy weakens or turns negative, gravity will seize absolute control. When Albert Einstein first introduced the cosmological constant in his equations of general relativity, the math allowed for this exact reversal. Recent data from dark energy surveys suggests that a shifting negative dark energy remains a distinct physical possibility. This cosmological timeline shows how that reversal would look. The volume of the expanding universe slows down, plateaus, and then sharply reverses direction, sending all matter rushing back inward. As space shrinks, it causes intense thermal compaction. Background radiation heats the vacuum to extreme temperatures. Galaxies collide, and surviving stars are cooked from the outside in. A defeated dark energy results in the Big Crunch, a catastrophic, fiery collapse that compresses all matter and energy back into a reverse Big Bang. However, a Big Crunch might not be a true ending. The Big Bounce hypothesis suggests this intense compression is what triggers a rapid rebound, acting as the ignition spark for a new universe. This chart plots our universe's current age against the vast scales of time we are actually dealing with. Regardless of whether we face a freeze, a rip, or a crunch, these executions require hundreds of billions to tens of trillions of years to play out. Compared to those chaotic future states, our current era is remarkably calm. Stars shine, galaxies interact, and temperatures are stable enough for chemistry to occur. We happen to be living in the cosmic spring. It is an extremely narrow thermodynamic window in the lifespan of the cosmos, where biology, thought, and observation are actually possible. The ultimate destruction of the universe is a mathematical certainty, but the fact that we exist in the exact moment to look up and understand it is a beautiful and lucky anomaly.